Hi, everyone. I'm Chichao Wang. Today, I'm presenting with my colleague, Joseph Severino. And the topic we are presenting is, let me move this view. Topic is high-fidelity modeling of curbside driving behavior in SUMO. And just a warning, it's a virtual conference this year, and we're having a virtual jet lag. Apologize if we start talking something nonsense. Start with acknowledgement. This work is being supported by US DOE and Dallas-Fort Worth International Airport. And we appreciate help from our collaborators and the technical team. In this presentation, start with introduction, then go to how we did the modeling, talk about simulation setup, then show you some animations, followed with what we observed, some numbers, some chart that we observed, and with occupancy, density, and then observed flow and waiting time, then wrapped up with conclusions. Well, nowadays we see more and more transportation network company or rideshare company vehicles on the road. And that's basically led to higher curbside usage. And imagine when you go to an airport, you just call for a ride, right? And then they do not, instead of you driving there, you will go to a parking lot, they may just drop you off at the curbside of the terminal. Then we basically see higher and higher curbside usage. However, curbside driving behavior is not where modeling most traffic simulation software, and that's resulting a different capacity from the reality. And we want to try to get more realistic behavior. This is animation that we recorded from SUMO with its default curbside driving behavior, basically let it park on the side. And then you will see the vehicle follow each other, and they don't know what happened downstream, and they will have a big queue there. And also in reality, when you if you've been to a very busy airport, you may see people do not behave that does not follow all the rules. They try to park on the rightmost lane, but in reality, people may just double parking, means that they may just stop on the left lane and do a quick pickup drop off. So what we did is we used Tracy and detectors to observe vehicle status and vacancy along the pickup drop-off edge. And then before we run simulation, we want to set up a trip file. And in that, we set a stop edge prior in the trip file so that vehicle will go to that edge. So, so far is everything default in SUMO. Then we reassign stop based on the real-time availability. Basically, if you are in a large network, you will still drive until you hit that edge you want to do a pickup drop-off. And then we'll reassign the stop based on what we see in the network. We randomly choose from the available spot downstream. And if the curbside is full, we can do double parking for extra stop. So on the right side is the flow chart. Basically, every time step, we will check first is the vehicle is on its pickup drop-off destination edge. They may have multiple, but if it's on any of them, if not, then we do nothing, just let it go. If it is on that pickup drop-off destination edge, then we'll check has the vehicle been processed. If not being processed, we first set it being processed, and then we remove the current vehicle stop. And if we find a downstream open curb space, then we just set a random downstream available photo spot as the vehicle stop. If there is no open space, then we just randomly set a photo spot as the vehicle stop. I see some question. Okay. And then so that is when the vehicle is newly entered that edge. But after it's entered the edge, things may change. Then we will check is the vehicle still moving? If it's moving, then good, keep moving. Is the vehicle at a stop? If it's already at a stop, then nice, it's already finished that its task. Then we check is the vehicle's stop available. Basically, if not moving, the vehicle is moving and it's not at the stop. And the stop is still available, then we'll go with the plan. But if not, then we will remove the current vehicle stop because it's not available anymore. And then we'll check is there a downstream open curb space, basically get here. And if there's a downstream open space, then we will assign the downstream open space to that vehicle to stop. If not, then we just set the current vehicle location as its stop. That is the part that allow double parking. Basically, when it's on the left lane, that's where it's drive. Well, actually, any lane that is not the rightmost lane, it's made to stop there. And if it cannot find any open space downstream, then it's made to scale up and set that current location as its stop. And then with that rule, we set up some simulations. We have this very simple geometry in the incoming lane, the pickup drop-off zone, and outgoing edge. And then the range of demand not to exceed the capacity of the two incoming lanes so that they can come. And we have various range of curbside spot. So here we set up these detectors. Each of the detector is slightly longer than the vehicle nest, so that when it's parked, they can comfortably get into that parking spot and leave. And in our experiment, we set between 10 and 80 spots. We ran over 10,000 simulations with different random seeds and run them in parallel on HPC. We have buffer zone at the beginning and end of the curbside, basically here, to prevent congestion. Basically, when a vehicle enters the edge, it cannot stop right there since it's already at a fairly high speed. So we set this buffer zone. And with that, we have another set of animations. On the top one is show when the demand is lighter, or actually similar to what we had in the previous animation by default. As you can see, it's running smoother with same holding capacity of the vehicle on the curbside. And on the lower figure, we can see that some of the vehicle can just stop right where it is, basically on the second most lane, and to try to mimic the real world behavior. And then the next one. Joey, want to take over?
Yeah, so we did some simple analysis of all these simulations to kind of see some metrics with the SUMO outputs, just to kind of see what the effects were. So on the right, I'm going to describe basically the X and Y axes so we know what we're looking at. So the top and the bottom both have X axes of the demand input for vehicles per hour. So these are the injected demand that you put in a trips file or a routes file for the flow on the actual network. On the top right, we see the edge occupancy. So this is in a percentage. Just something to note here is that this is kind of limited by your minimum gap. So depending on what your min gap is, that'll tell you how high up how close it gets to 100%. In these scenarios, we just use the default min gap for these. So for the top, what you'll see here in the blue line is the improved Puto behavior. And then in the gray line, the gray dashed line, that's going to be kind of the default SUMO behavior. So we can kind of clearly see here that a delineating point is at 1,500 vehicles per hour, and we see that the improved behavior increases quite a bit more and is much greater of occupancy compared to our baseline or the default behavior. Now, if we go down below, when we look at the edge densities, so that's the number of vehicles per kilometer, we also see the same behavior where the improved behavior goes all the way up to about 160, 170 vehicles per kilometer compared to the default, which maxes out around, it looks like about 60, and then comes back down. So we can see again right here, about 1,500 vehicles per hour is kind of where it flattens out or plateaus. And then if we can go to the next slide. All right, so then the next thing that we end up observing here is the observed flow and then the waiting time. So observed flow here, as opposed to the demand input, is going to be how much flow is actually getting through that edge. So ideally, you would want to see the observed flow to be directly linear with the demand input. And you can see that on the top one that it does look pretty linear up to about 1,300 or even 1,500, and it starts plateauing off. Again, this is kind of a threshold point that we saw. So in the blue, again, this is the improved behavior, and we see that it's well above the default behavior for the observed flow, which alludes to a higher capacity. And we also see that the variance in the lighter blue is much smaller than the variance in the gray. So the gray area has a much higher distribution or higher variance amongst all the simulations. So if we go down to the waiting time to be kind of a correlate for delay, we can also see here that the waiting time is far less up to the 1,500 vehicles per hour for the improved behavior compared to the default. And it seems to have also a lower variance as well. So it seems a lot more stable for the waiting time. So with all of this, we can kind of conclude a little bit more that we improve the capacity, which is basically what we're trying to get at for our larger simulations of DFW, is to kind of have a more realistic capacity on here. So the main conclusions to pull from this is that we have a high resolution accurate modeling for vehicle curbside behavior. It's a lot more realistic as well compared to the default. We use some randomized pickup drop-off locations for selection, and there's some awareness of the vehicles to see the free slots downstream for the pickup drop-off areas as opposed to the default, and vehicles saving time by double parking. So I'm not sure if that's common in Europe, but we definitely get some double parking scenarios where people are a little bit more anxious and they're willing to break the rules for these kind of things. So we wanted to incorporate this kind of anxiety that people end up having. And then last is simulation results that compared to the improved curbside behavior versus default behavior show that the improved curbside behavior exhibited more realistic and increased the curbside capacity, utilizing the capacity and utilization while maintaining the same vehicle delay time. So thank you guys for your time, and if you guys have any questions, we'd be happy to answer those for you guys.